Hello, Namaste, welcome to this channel Dr.ARM's Chemistry. Friends, we were discussing the crystal field theory with respect to various types of complexes, and last time or in the previous lectures we have discussed the crystal field theory in case of the octahedral and variety of other tetrahedral complexes. Today we are going to see the crystal field theory in case of square planar complexes. A square planar structure is like this. So we can show this as a square planar structure. In this structure, metal ion is at the center. So this is a metal ion, and this is about the ligands. So ligands are occupying these four corners. Ligands are occupying these four corner positions. So we can show these bonds between the metal ion and the ligands in this field. So if we consider the axis, so these are the axes. So we can say this is x-axis, this is y-axis, and there is z-axis. This is z-axis. So you will find that the crystal field shows that there is no ligands occupying in the direction of z-axis. So in order to obtain such structure, we have to remove, say for example, if we consider this is a octahedral structure. This is a octahedral structure. Then we have to remove these ligands which are existing, or in case of this is in case of octahedral structure. So we are removing these ligands. So because of this, the structure is reduced to this. So you can show that because of such removal, the structure is converted into this square planar structure. So the two ligands occupying the positions in the direction of z-axis are removed. So the ligands there are only four ligands remaining in the structure like this, and two of these ligands are occupying the two positions in the direction of x-axis, and two ligands are occupying the positions in the direction of y-axis. So because of this, the structure is stabilized when the orbitals. Now if we see the structure, say this is the energy axis, and in case of this octahedral structure, you will find that the P to G ligands are low lying, whereas the EG ligands are high energy ligands. But in case of this square planar structure, we have the structure in different manner. So we can observe that out of this octahedral structure, we can have the if we extend this, and this is further divided into, means the crystal field is split in order to obtain the square plane structure. During this splitting, the orbitals which are lowered here are two, which are d and one is high energy. So these two orbitals are d zx and dy z, and this is dxy. Then in other EG structure, if we take this EG structure, then it is also divided into two, means the energies are lowered in this way. So this is d this is dz2 and this is dx2 minus y2. But when the ligand field is increased, when the ligand field means when the strong field ligands are used, then the splitting is also changing, means that there is some distortion. The energy of these structures is lowered. So we can show this in this way. The two orbitals dxy, dx or dzx and dyz are lying in this way. Then this dz2 is further lowered in energy. So this is lowered in energy to a greater extent. So this is dz2. Then energy of this dxy, which is in the plane, the xy orbitals are lying in the plane in which the dz2 and dx2 minus y2 are present, and that is why the energy of these orbitals is also increased. So that is moving up. So we can show this as dxy, and this dx2 minus y2 is also further rising in energy. So we can show this as rising in energy in this way. So this is dx2 minus y2. This is dx2 minus y2. Now if we see the energy difference between these. So here the energy difference between these orbitals is delta. This is delta octahedral, like octahedral. Then the energy difference between these two orbitals is 2/3 of delta O, and this energy difference is 1/12 of delta O. 1/12 of delta. Now, if we see, while the formation of square planar structure, the orbitals which are lying in this direction are not showing any kind of repulsive force or interaction with ligands, because there are no ligands lying in this z direction. There are no ligands. So the dz2 orbital is showing no interaction. Its energy is not raised. However, its energy is lowered to greater extent. That is why it is lowered in this way. Whereas this dxy which is lying in the same plane, is showing strong interactions with the ligand orbital or ligand electrons, and that is why the energy of dxy goes up and it is higher than this z2 by the factor of 2/3 of delta O, and here delta O is crystal failure splitting of octahedral crystal failure. dx2 minus y2 orbitals are lying in this direction. Two orbitals are lying in this direction. Two orbitals are lying in this direction. Means two lobes. We can say dx2 minus y2 has 4 lobes. So these out of 4 orbitals are lying in the direction of y-axis, and 2 lobes are lying in the direction of this x-axis. So in this way, they suffer strong interaction with electrons of ligands. As a result, their energy is highest or very high, and it is defined as delta O. So the symmetry of these orbitals. Now here we can see these orbitals remain in the plane or in between. So if we see this dzx orbital, it is lying between the axis x and between the axis z, and that is why it is called a dzx or dxz. Similarly, the dyz orbitals have lobes lying in the direction or in the plane between the y-axis and z-axis. So you can say this is y-axis, this is z-axis. So there are orbitals like this. So they suffer less interaction, and that is why they are lying lowest in the energy level diagram. Now if we see the symmetry of these orbitals, it has EG symmetry, it has EG symmetry, it has G2G symmetry, A1G symmetry. If we see the symmetry of these orbitals, we can show this as EG symmetry. This has A1G symmetry, A1G symmetry. This has B2G symmetry, and this has D1G symmetry. With respect to symmetry, the symmetry is shown by these orbitals in this way. The symmetry of the square planar structure is shown as D4H. D4H. So the octahedral symmetry is changed to D4H symmetry in this way. Now we will see the example by which we can explain various properties of such structure. For example, if we take the complex Ni CN4 2 minus. So this is D8 configuration. This methylamine is having D8 configuration. So you will find that this ligand is strong field, and if we distribute these electrons here, we can find the electron distribution like this. So in square planar structure, so we can show the comparatively square planar as well as tetrahedral structures also. Now we will show here for our convenience the structures. So if it is a square planar structure, then we have the orbitals like this. So we have shown the sequence of these orbitals. So first of all, we are having the low energy 2 orbitals then this dz2 orbital, then this dxy orbital, and then there is a large difference. So we can show this as this dxz, dyz. This is the dz2, this is the dxy, and this is dx2 minus y2. Now if we show the electrons, distribution of these electrons, then we can show this distribution in this way. So we have shown 4 plus 2, 6, and these 2, 8 electrons in this way. So there is, because of such distribution of electrons, there is no unpaired electron. Hence this complex is diamagnetic. Diamagnetic. And it is also called a spin pair. Spin pair. Now, if we see the comparative, for comparison, if we see the structure, tetrahedral structure, then we can show these Eg orbitals and these two T2G orbitals. So this is for tetrahedral crystal field. For comparison, we are showing this. The 8 electrons are distributed in this way. So 4 plus these 4. So out of it, the 2 electrons are unpaired. So this complex is paramagnetic. Paramagnetic. Because 2 electrons are unpaired. Now for this purpose, we can have the example. So for this purpose, we can have the example NiCl4 2 minus. So we can have this example NiCl4 2 minus. So this shows the distinction between tetrahedral and the square planar structure. So we will show here square planar structure. Square planar crystal field. So you will find the difference. This is totally diamagnetic. There is no unpaired electron. So it has no paramagnetic behavior. But there are 2 electrons unpaired, so it is paramagnetic. So distribution of 8 electrons here is based on the splitting of these orbitals. So here, in the same way, we can consider here. So you will find that this energy difference is much larger. The energy difference is different in different stages because there is no uniform, means there is no division of the orbitals undergoing splitting in 2 parts, but it is in more parts. That is why the difference is different in between the different orbitals, and this is shown here for our reference. In the same way, we can have the complexes. In second row, third row, metal ions. Second and third row of metal, the metal orbitals, having D8 configuration. For example, platinum. So the metal ions having such type of structure is given by the platinum 2 plus, palladium 2 plus, then RH, rhodium, RH plus 1, and IR plus 1, IR plus 1. So these metal ions can give same type of distribution, which are, these elements are from lower d orbitals, that is second and third row of d orbitals. So here the square planar and tetrahedral structure can be experimentally compared using these two examples. So one can compare the square planar and tetrahedral structures. Taking this example of D8 configuration, say a line forms first row of transition elements, then second row, third row. So in this way, these examples can be illustrated. So with this we will stop our discussion here. Please subscribe to this channel. If not, then I request also you to please, if you like this video, please press the like button also and bell icon, or you can put your comments. How do you like this video? If you can also put your suggestions regarding the contents you are required for your study. So see you next time. Thank you very much for watching this video.